Hey everyone, welcome back to Chemistry 1111 with Dr. Carroll here. We are going to look at gas laws from a molecular standpoint. So this is molecular view of gases. In our textbook, we're on page 77. We don't look at all aspects of this topic, just a few, and it's interesting stuff. We start with molecular speeds. Well, if I'm looking in this room right now, I see all sorts of molecules. No, I don't see many in the gas phase, but they're going to go at a distribution of speeds. Okay, there's a way to collect them, a molecular beam apparatus, but let's jump straight to the important picture here, figure 210, which shows that the faster molecules have the lower molar mass. As you see here, hydrogen, it's almost a bell-shaped curve here. At a given temperature, 300 Kelvin, we see a range of speeds. You could make it kinetic energies if you want, 1/2 mv squared. But the point is that the hydrogen has a faster, it's called a root mean square speed, than does the methane, than does carbon dioxide, because carbon dioxide has a larger molar mass value than methane, which in turn larger than hydrogen. So something less massive is going to travel more quickly. Okay. We can relate speed and energy, remembering that the kinetic energy is 1/2 mv squared. So if you know the most probable speed of hydrogen at 300 Kelvin, 1570 meters per second, the most probable kinetic energy would be, well, first let's get the mass of a hydrogen molecule. So we're going to divide by 6.02 by 10 to 23. Now this has to be kilograms, not grams, so that you get joules. So that's sometimes a tricky thing here. You forget to convert grams to kilograms here. And you get 4.13 by 10 to minus 21 joules associated with every hydrogen molecule. That's the most probable kinetic energy. Okay? Now, if I get the most probable kinetic energy for the other gases, the methane and the CO2, they turn out to be the same, which means that your most probable kinetic energy is proportional to temperature, and that's it. Okay, which is an interesting point. So even though the speed distributions are different, the most probable kinetic energies are identical since the temperature is the same. Okay, now we can talk about the average kinetic energy. A bar over the symbol means average. In this textbook, another textbook, it's different. So it turns out that the average kinetic energy for a mole of something is 3/2 RT. So you see that the molar kinetic energy on average is 3/2 times the gas constant times the temperature in Kelvin. So you'd be given these equations if you needed them. Sometimes they appear, sometimes it's just more of a qualitative nature. But let's try an example here. Determine the average molecular kinetic energy and molar kinetic energy of gaseous sulfur hexafluoride. So the molar kinetic energy you are not going to be dividing by Na. So we want the constant R and Na as well as the temperature. The constants are found. R is 8.314 joules per mole per Kelvin. Okay, that's one of the values of R. That'll become more important as we go through the course. And there's my Avogadro's number. So convert the temperature to Celsius. Sorry, to Kelvin from Celsius. So per molecule, your average kinetic energy is, notice I don't even know what molecule it is. All I know is that it's the average kinetic energy is proportional to temperature. So it's 8.76 by 10 to minus 21 joules per molecule. If I multiply by Avogadro's number, I get 5.28 by 10 to the 3 joules per mole. Really, I'm not using sulfur hexafluoride. I'm not using the molar mass at all. So if I did another molecule, I'll be okay. Does it bother you to find that neither the chemical formula nor the molar mass is needed? Remember that not all data are necessarily required for any particular calculation, because average kinetic energy depends on temperature but not on molar mass. We do not need mass information to do this. And then I could try one with molecular nitrogen. Shall we try that one? Let's see, 2.14. Yes, okay. So the kinetic energy for a molecule, minus 35 degrees Celsius, so I'm going to take minus 35 plus 273. .238 Kelvin. Okay. So then the kinetic energy is going to be, average kinetic energy is 3/2 times R, 8.314 times 238 divided by 6.02 by 10 to the 23. So 1.5 times 8.314 times 238 divided by 6.02 by 10 to the 23, 4.93 by 10 to minus 21 joules per molecule of nitrogen in the jetliner. And for a mole, the average kinetic energy molar, I'd multiply by the molar mass times 6.02 by 10 to the 23, 2.97 by 10 to the 3 joules per mole. Okay. Now, let's get a bit descriptive here. The behavior of gases suggests that molecules have little effect on one another. Gases are easy to compress, showing that there's lots of empty space between them. Gases also escape easily through any opening, that's known as effusion, indicating that their molecules are not, we won't get much into that, but it is called effusion, or pinhole effusion, indicating that their molecules are not strongly attracted to one another. An ideal gas is defined as one in which both the volume of molecules and the forces among the molecules are so small they have no effect on the behavior. So another way to say it is the molecular volume itself is a lot smaller than the space in which the molecules occupy, and the intermolecular forces are very weak. The more a gas is like that, the more we can say it's ideal. Okay. Small molecules usually have small attractive forces, and they're more likely to be ideal gases than larger molecules. Mostly small molecules with molar mass less than 50 grams per mole are considered to be ideal. So here we have a list of some common gases and their molar masses. I rhymed. Common gases and their molar masses. Okay, and so all these ones here are at roughly room pressure and temperature, are good contenders to be molar gases. And okay, this part here I'm not going to care much about. You can read that on your own. But I just wanted to talk a bit about ideal gases. Now, if the pressure, let me just put this in the margin here, if the pressure goes up and temperature goes down, then deviation from ideality increases, and what we say is the gas becomes more and more like a real gas. Like when Pinocchio wanted to become a real boy, gas becomes like a real gas. Ooh, it looked like a lightning bolt just ran through the house a second ago. My goodness. Okay, you can try these section exercises on your own. And so let's look at some additional gas properties, and then we'll look a bit more at real gases. And you could have done this a bit earlier. We can determine molar masses and gas densities and how fast reactions go. So I'm going to jump now to page 84. And determination of molar masses. We know that N is PV over RT, but we also know that the molar mass is M over N. So then we can write that the molar mass is MRT over PV. Okay, so the molar mass is MRT over PV, combining these two together. Or let's just write it out. Molar mass is the grams, and a little m for grams. R is the gas constant, T over pressure times volume. So here's a useful equation. If I know how many grams of some molecule I put in a bulb, I know the volume of the bulb, I know the pressure exerted by the gas molecules in the bulb, and I know at what temperature this is happening. Well, R is a constant. I can determine the molar mass. Let's check the units. Mass is grams, R, liters, kilopascals per mole per Kelvin, temperature in Kelvin, divided by pressure, let's say kilopascals, volume in liters. So liters cancel, kilopascals cancel, degrees Kelvin and Kelvin cancel, and I get grams per mole, which is exactly the unit of molar mass. Okay. Now, I see here a little note here. No, I guess I can do this one here. Okay, so calcium carbide is a hard gray black solid that has a melting point of 2000 Celsius. This compound reacts strongly with water to produce a gas. No, this is way too much detail. I don't need to do this. Let me jump and do a different question instead. Do 2.45 instead. Okay. I'm going to do question 2.45. So I'm going to go to Paint here and do a question from the end of the chapter, which apparently is going to be better. So let me jump to 2.45 on page 105. It's all about Freon. Here we go. We have a 2.55 gram sample of a particular Freon. We don't know what it is. It could be a mix of elements to make the molecule. So there's different Freons. Anyways, the mass is 2.55 grams. The volume is 1.50 liter. The temperature is 25 degrees Celsius, which is 298 Kelvin. The pressure is 262 torr. Okay, I want to convert that to kilopascal. Oh, what was that again? A torr Let's jump back. I know. Where's my index card? 1 torr is 133.3 pascals. So 1 torr would be 0.133 kilopascals. Okay, so I'm going to do 262 times 0.1333 is 34.92 kilopascals. Okay, so now I've got the pressure and I got all this, so we can get the molar mass. Molar mass equals, well, what was the equation I just written? Let me go up a bit. MRT over PV. MRT over PV. So 2.55 times R. What R am I going to be using here? Liters, kilopascals per mole. What R is that? Always got to check our R's here. 8.314. Okay. Liters, kilopascals per mole per Kelvin. Temperature is 298. Pressure is 34.92. And volume is 1.50. Okay, so 2.55 times 8.314 times 298 divided by 34.92 times 1.50, 120.61 grams per mole. So that is the molar mass. Okay, now it asks something else here. It says, what is the formula for the compound? So it's a CFC, which means it's got carbon, chlorine, and fluorine in various amounts. It's going to be 120.61. So we actually have to think a bit here. Carbon is 12, chlorine is 35.5, fluorine is 19. So how can we get to 120 here? Well, I could do 3 fluorines, 35, 70, 100. No, that's going to be too much. So it can't be 3 chlorines. How about 3 fluorines? 57 and 79 and 35. Will that work? 79 plus 36 roughly. I'm just guessing around here. 115, that's close, but not quite. What about 2 chlorines and 2 fluorines? I know that there's only 1 carbon, by the way. So 35.5 times 2, so that's 71, plus 19 times 2 is 109, plus 12 is 121. That works, right? So it's CCl2F2. CCl2F2 would be our answer for 2.45. Now let's forget, are the problem answers at the end of the chapter? No, they're at the end of the book. Okay, so let's double check 2.45. This is also called an ILW, which means interactive learning workshop or something like that, which means you can do it in your widely expressed 121 grams per mole CF2Cl2. Widely expressed, is that what they call it? Something like that. So that's 2.45, and that was a good question, I thought. So I'm going to do another one related to density. So that was an example of how to get molar masses. Okay, so now let's go back. Should we go to the slides? We haven't been to the slides in a while. Let's see, do the slides give us anything different? Ideal gases, gas. Okay, well the density, well I'm going to get that from here, so not really. So let us get the density of a gas, and density of gas is going to depend on the temperature and the pressure. Liquid solids, oh, we got all sorts of things going on. Oh, I'm getting spam messages. Whereas liquids and solids densities are not strong functions of temperature or pressure, the density of a gas varies strongly with these conditions. So let's combine some things here to get the density. Density in units of grams per liter or kilograms per liter, depending on what we're talking about. So we know that grams over molar mass is PV over RT, and then density is M over V, so it's PM over RT. So that is density. So the density of the gas, which can be represented by the Greek letter rho, RHO, sort of an italicized letter P, is going to be pressure, well I write it like this, pressure times molar mass over R times T. That equals the density. So at a given temperature, for a given molecule, if you have greater pressure, you're going to have a greater density. If the pressure stays the same for the given molecule, if you have a higher temperature, the density is less, right? Hot air balloons rise because hot air is less dense than cold air. That equation tells us. If you have same conditions of pressure and temperature, then if you have a heavier gas, one with a greater molar mass, it's going to be more dense. It's not going to rise up as quickly. And in Bhopal, India, in the mid-80s, there was a horrible industrial accident where the gas that was produced in a accident was heavier than air, so it killed people because it was poisonous and did not disperse quickly from the accident site. So density is an important thing to understand, and we see the effect of things here. Now let's just check our units here. So pressure, let's say it was kilopascals, molar mass is grams per mole, and then R is liters, kilopascals per mole per degree, and temperature is degrees, so those cancel. The per moles cancel, the kilopascals cancel, and you get units of grams per liter. Again, there are times when we want to convert to kilograms per liter, but for now, yes, the density works in terms of grams per liter. All the stuff I just said is mentioned in those 3 points, so that's good. Bit of practical stuff. When gas is released into the atmosphere, whether it rises or sinks depends on its molar mass. If the molar mass is greater than the average molar mass of air, the gas remains near the ground. Carbon dioxide fire extinguishers are effective because of this feature. They stay near the ground. Molar mass of CO2 is greater than nitrogen or oxygen, so it lays down a blanket of this gas. That's a nice analogy. It lays down a blanket that excludes oxygen from the fire, snuffing it out. Okay, and here we have a hot air balloon analogy. Are we going to do this one? I guess we can do it. And then it says do 2.47 after. Okay, fine. So a hot air balloon will rise when the density of the air is 15% lower, at least 15% lower than that of atmospheric air. Calculate the density of air at 295 Kelvin and 100 kilopascals, assuming that dry air is 78% nitrogen. That was by volume. We'll find out. And 22% oxygen. First, we have to calculate the density of atmospheric air. So, the molar mass of dry air, well, okay, so this is a mass percent. These are mass percents. So it's 78% by mass of nitrogen and 22% by mass of oxygen. I know there's some other smaller amounts, but we're neglecting that. We're rounding that off for now. And then we get that the density of the gas at 295 Kelvin is 100 kilopascals is the pressure we're talking about. There's our molar mass of atmospheric air over RT, so 1.18 grams per liter. Okay, so now the balloon will rise when the density is 15% less than the density of exterior air. So if it is 1 gram per liter, okay, so we want it to be 1 gram per liter, not 1.18, but 15% less than 1.18. What does that mean? 1.18 minus 15% of that. So 1. So I know what I want the density to be, and I have these other values. So the question says, at what temperature will this happen? Around 350. A temperature of 350 is 77 degrees Celsius, a reasonable result. So the balloon will rise when you have the air hot. How hot? At least 77 degrees Celsius. Interesting. So that's actually a practical thing to do. I've never been on a hot air balloon ride. I once threw a water balloon at someone and missed, but I've never been on a hot air balloon ride. But some of you have. Next time you go on, you can try that out. And the blimp one you can try on your own as well. Let's try 2.47 at the back of the book. Sorry, at the back of the chapter, because that's a density one. What is the density in grams per liter? Okay, so this is, let me go to a new paint here. So page 106, 2.47. There's a storm happening outside right now. Maybe not where you are because it's a different day, but where I am. Page 106. Number, the dogs are freaking out. 2.47. What is the density of SF6 gas, sulfur hexafluoride, at 755 torr and 27 degrees Celsius? So SF6, so 300 Kelvin at 27 degrees Celsius, 755 torr, so that's 755 times 0.1333 is 100.64 kilopascals. Okay, so I want to find rho, so it's pressure times molar mass over R times T. The molar mass of sulfur hexafluoride, I don't know that off the top of my head, no. So let's find it. Sulfur is 32.07 plus 6 times 19 for the fluorine, 146.07. So 46.07. Pressure 100.64 times 146.07 over 8.314 times 300. 100.64 times 146.07 divided by 8.314 times 300. Okay, 5.89. Okay, and that would be units of grams per liter. And that is correct. Okay. So let's go back to the mini text here. going to do these things here. Let's see. So those are density questions. No, the other stuff is in 2.6 we don't worry about. So let me finish the chapter here and go to 2.47. So Graham's law. Now I'm saying that, and some other prof might throw it in at the very end, so I may have to jump back and do this, but I don't think so. Non-ideal gases. So as we said before, if you have a non-zero intermolecular force of attraction, which all systems have, then you won't have an ideal gas. The truth is, the plain cold truth is that there is no such thing as an ideal gas. But we can come close to that if we have high temperatures and low pressures, because then our intermolecular forces are very small, very weak, and our molecular volumes are very small compared to the volume occupied by the gas. So that's all this is saying. And you can have deviations from ideality, and van der Waals equation can be plugged in to get different values, to get corrections from ideality. And that's usually, we don't do any more calculations. It's just a qualitative thing. If it gets quantitative, I'll talk about it, but we hardly ever do, so I'm not going to bother with it now. Chemistry of the Earth's atmosphere, I don't care about. Well, I care about it, but it's not in the test. And so some of this other stuff is good. Here's your visual summary for the chapter. So we see the different parts, and it's always good to have those there. You see the equations summarized. You see just a bit about van der Waals equation here, that P is nRT over V, but you have that little correction factor in this correction term. So you have two correction terms to show that gases are actually real. There's no such thing as an ideal gas, even though we use these ideal gas equations to give us a rough idea on how things work. Okay, so there's lots of end of chapter questions for you to try to become experts in all this, and that's lecture 3, and most likely the final lecture in this unit. Have fun.